Hello and welcome to this presentation on TUFLOW and some pretty exciting new features that we're building in and the integration of those features into 12D model. The agenda for today's presentation is two big ones, which is the Subgrid Sampling feature and the Quadtree Mesh feature. So both of these have really allowed us to improve how we model our urban areas, but also catchments and other things. They are really a game changer to the hydraulic modeling of surface flow. After the Quadtree Mesh part, Rob Graham's going to give a bit of a demo, but then we'll show some other interesting stuff, maybe not relevant to everyone, but non-Newtonian dam break feature in TUFLOW, and just some early outcomes out of a bridge deck joint research project with Department of Main Roads in Queensland that's aiming to improve how we model bridges much better than we have in the past. Today's speakers are Rob Graham, who many of you will know, and he's been the principal person behind the 12D TUFLOW interface, and myself, Bill Syme, I've been working with TUFLOW a very long time, and now lead a team of about 12 or 13 people servicing the TUFLOW software user base. So, subgrid sampling, what is it? What does it mean? Well, to try and explain that, I'll just briefly talk about how things have always typically been done for many, many years. And that is to break up your surface area into cells. So here we have a square cell, and then we need some elevation data associated with that cell, and we typically historically have just sampled a single elevation in the center, and that gives us effectively a square tub that will hold water. And then for how the water moves around from one cell to the next, we sample a single elevation in the middle of the cell side and just use a flat rectangular section. And that's nice and simple and has worked well. And where your underlying DEM or tin is of not dissimilar resolution or doesn't vary much in elevation, that's fine. But sometimes you start to miss out key features. So in this case, we've got a swale going down the side of a road, and we're not going to really capture that very well at cells of that sort of resolution. And so what subgrid sampling is, it's basically instead of just sampling single elevations at the centers and the mid sides, we're actually taking a high resolution sampling across each cell. Then instead of using a single point, giving a rectangular section on the sides and a square tub approach, we actually generate a relationship or curve, which is effectively the cell volume with height and also the flow area for each cell side. So in other words, the air for very shallow flows, you're going to be operating down in these levels here, and you're going to have a better representation of what's actually inside that cell in terms of topography. So a way to visualize this is on the left here we have your raw topography, nice high resolution data, and how a traditional approach model would see that data is basically something like this. So just a whole bunch of square cells, flat bottomed and square sides, rectangular sides. When you apply SGS to that, and particularly if it's a similar sampling interval to your DEM or tin, then this is how your model sees it, in much more detail and a lot more accuracy when your cells are quite large relative to the changes in terrain. So what does this mean for our hydraulic modeling? Well, we've been doing lots of benchmarking on this, and this is one of the nice little examples. So this is actually from a flume experiment. We've got a U-bend, it's about 1.7 meters wide, does a complete 180-degree turn. We've got flow coming in through this side, goes around here and comes out this side. So a nice little simple experiment carried out by De Vrend in 1978. So what they measured were the water levels, among other things, at each of these dots. So they've measured the water levels on the outside of the bend, the orange dots, water levels on the inside of the bend, the grey dots, and water levels down the centre. And this is the flow is going from right to left on this chart, and what you tend to see is on the outside of the bend, the water level tends to be higher, so that's around here. So the inertia of the water coming around the bend pushes it up higher on the outside of the bend, and to compensate for that, there's also a set down or lower water level on the inside of the bend, and down the centre is fairly uniform. So they're the measurements that were actually taken from this test. So if we model that flume and not using subgrid sampling, what happens is around this outer boundary, because we're using a regular mesh, you get this sort of distorted velocity pattern. So you see the water's sort of changing direction, it's hitting these bumps which aren't really there, but it's hitting these edges in the model because this whole cell is dry and this cell is wet. And what that does, it produces pretty terrible results. So what you're seeing here is the model results. And so the model came up with this up and down sort of water level profile as water worked its way around the outside edge, that very bumpy outside edge. And it didn't match the recorded measurements at all. And you can see the grey is on the inside of the bend and the blue is down the centre. And probably most importantly here is that the head drop across, the water level at the upstream end is much higher than what was measured. And that's because the water's finding it harder to work around this bend. So it needs a higher water level, a higher energy level to push that water around the bend in the model. Now let's see what happens if we run this with subgrid sampling on. And what you see around the outside edge, because these green cells are all now partially wet, like this cell is mostly wet, like this one's mostly wet, whereas this cell here would just be a tiny bit wet. This one here, a very tiny bit wet. But what it does, it makes the streamlines around the outside nice and smooth, just how they should be. And if you look at the results, this is what comes out. This quite good comparison, particularly given we're running a regular grid. So this is the outside bend, inside bend, and down the center. And probably most importantly, we actually match the head drop across this bend, which means if you're modeling a real world scenario, you're going to be much more confident about your results. The other benefit that subgrid sampling has, and basically subgrid sampling is more influential when the size of the 2D cell is much larger than the underlying data, the underlying DEM or tin. So if we simulate this model with a 34 centimeter resolution, and this is 1.7 meters, so there's about 5 cells across here. And if we look at the results, this is what we see. Not too bad, a bit bumpy, and that will be due to the coarse resolution of the model. But really importantly, the upstream level is actually matching what was measured. So the energy drop across that bend is consistent with what was measured, even at a very coarse grid like 34 centimeters. If you look at the results for 17 centimeters, same again, good match upstream, but smoother outcomes, so that's nice. And if you keep going finer and finer, basically you keep getting a nicer outcome. So depending on what your objectives are, if you want to get that high resolution velocity, so then you do have to run with a smaller grid. But if you're just after a good match for the head drop around that bend, you could actually even model this situation on a very coarse mesh. So what is it? The other big plus we've found is what it means for fixed grid models when they're orientated, well, even for other types of models. So here we have flow down a rectangular channel, a very simple model, the slope of the channel is set so that there's a constant depth of 1 meter down the channel. You'll see two types of lines on these plots. One is a solid line and a dashed line. The dashed line is the energy level, so that's your water surface plus the kinetic energy of the water, which is V squared on 2G. And you'll see here, this is the result for just when everything's aligned and everything's nice and perfect. And you'll see that the results are matching the 1 meter exact answer very precisely. So that's great, that's excellent. Always happy with that. And these simulations are without subgrid sampling. As soon as you start to orientate the grid, you get the same issue as we saw with the U-band test. The water is finding it hard to work around these, these corners in the mesh. And so the streamlines are going in and out, and consequently you tend to produce a higher water level to push the water down this more rough representation. And so you start to deviate from theory, and that's not good. And if you go to 30 degrees, it gets even worse. So the coarser your mesh, the worse it's going to get. And yeah, that's always been a known problem, particularly with fixed grid meshes. Let's rerun those with subgrid sampling on. There's that no change, of course, with everything's aligned, no problem there. But when you move to the angled ones, you're starting to get that nice streamlines inside. All these cells that are along here are partially wet. They're sort of shown fully wet, just to give, that's just how the output comes out. But you can see that these are all partially wet, and you are starting to match pretty well exactly the results. You go 30 degrees and you still have a good match. And so what we've been seeing is with subgrid sampling, you're starting to get, well, you are getting mesh orientation in no dependency on that. And that's really, really important, particularly for fixed grids. So as an example, here we have a little model in 12D. It's a roadway. And what it means is that we can orientate that model in any way and maintain consistency in our results. So if you take a profile across the gutter, and in this model only the gutter is flowing, so it's tiny, and it's pretty well one cell. Here's the cell width here, one cell across that whole gutter. Without subgrid sampling, the results are terrible. But with subgrid sampling, you can rotate this grid in any orientation and get consistent results. That's really, really important, and it really has improved things enormously about how we can model these sort of fine features such as gutters. Yeah, as I said, the water levels are, just beautifully consistent. Really nice. So we've been seeing many benefits, but one of the benefits is subgrid sampling is helping enormously with the inlet flow capture. So basically the inlet flow capture is a function of either the depth at the inlet or the approach flow. And those two things can be related depending on the grade. With subgrid sampling, we're getting much better pit flow capture because we're basically coming in higher on the curve to get the capture flow. Without subgrid sampling, you don't capture the right amount of water very well. Plus your water levels will be up and down, and it's a very poor representation if you have a coarse grid. If your grid is fine enough, subgrid sampling is not such an issue or benefit, but if the grid is coarse, particularly if you only have 1 or 2 cells across your gutter, then that's a real problem. And subgrid sampling is really helping to solve that. So just the benefits of subgrid sampling. The first thing to note is that our previous way of dealing with this has always been to use smaller cell size, but there's a huge downside to having smaller cell sizes. Your run times go up through the roof. Basically, if you halve your 2D cell size, you increase your runtime by a factor of 8. You have 4 times as many cells and half the time step. So that causes a very large increase in runtime, just a simple halving. The other consequence too is you have very large output files. So that's sort of how we've try to get around this problem of having a coarse resolution, say along a roadway. But with subgrid sampling on, we're getting consistent results for different cell sizes. And what that means is that you can use much larger cell sizes than before and giving much faster run times. The other big plus, as we saw before, is that you can orientate your grid in any way and you'll see consistent results again. So you don't have to, you really don't have to be that fussed about the alignment and aligning it with the road and things like that. Another sort of benefit, and something to very much note for those people who've been using TUFLOW with 12D, is that there's no need for gully lines. In fact, if you put a gully line along a gutter, it can now be detrimental if you have subgrid sampling on. So, because basically with subgrid sampling on, it's picking up the fine detail in the tin or the DEM. So you don't need to try and roughly reproduce that by using gully lines. And as I've mentioned before, we're getting much more accurate inflow capture, which is excellent. So basically, subgrid sampling is a huge step forward for urban modelling, as well as catchment modelling and other applications. It's a game changer. Quadtree, that's the other big feature we've come out with. So what is Quadtree? Quadtree is basically the concept of splitting one 2D cell into 4. So here we've divided this cell into 4, and this cell, and this cell, and this cell. And again, you can keep dividing and dividing, dividing, and again. So it's a very simple concept. Basically, you're just allowing your 2D model to have variable cell sizes based on a subdivision of your square cells down and down and down. The beauty about Quadtree is that it's very, very easy to set up. And it's just simply a matter of using existing polygons like a road layer or drawing polygons. And you give each polygon a level of resolution, if you like. In TUFLOW world, 1 is the largest, and at the moment we can go up to 9 levels. We can go higher, but that means we have to switch to a double precision way of approaching the numbers. And we've yet to find anyone who's gone that high. So that's a huge change if you go to 9. And so effectively what it is, you might have a base cell size of at level 1, which is this cell size here. You can just draw a polygon and generate those cell sizes. And you can do another one, and you can do another one, and you can just keep going down like that. The other nice feature is that you can, if you want to skip one or more levels, you can have TUFLOW automatically transition the Quadtree mesh. It is a requirement that you can only go from 1 cell to 2 cell faces. So you do have to have these transition cells, but you don't need to generate buffered polygons to do those. TUFLOW will automatically generate those in between resolution cells for you. So if this is your area of interest and you're not really fussed about how quickly you transition, just have one polygon and your base level 1 cell size, and away you go. Here's a little example. So we have a nice little proposed urban area on a greenfield site. We would like to get our roadways at a level 3, a couple of levels finer than our base level. So we just have outer domain, which is the blue rectangle, so it's level 1, and then a polygon of the roadway, which is level 3. Digitize those in, and from that you can generate a mesh. That will happen automatically. So you can see it's got finer 2D cells inside the roadway and coarser here. Now if we zoom in to say this area here, you can see there's the coarser cell sizes. It's automatically transitioned from level 1 through to level 3 with some level 2 cells, and away you go. Very, very easy to do. So the pros and cons of Quadtree are that it allows you to get refined results where you need it. So here we want to get finer results around the roadway, the gutters. And also, in this case on the right here, we've got some little detention ponds, and we can get a finer resolution around those and coarser resolution away from those. So the beauty about it is it's very, very easy to set up, as I've just shown, and you will generally get faster simulations, and that's because you have less 2D cells. So the way to think about it is, I don't need a fine mesh out here away from the road, so let's make a coarser mesh. And typically what we're seeing is existing models which are the same cell size across the whole area are typically 2 to 5 times faster to run, just because we can have a lot less 2D cells. The negatives, well, generally speaking, it's hard to find a negative with Quadtree, but you can increase your run times. If your non-Quadtree model, for example, was at this resolution out here, and then you've started to put all this fine resolution in, that your runtime will increase because you're not reducing the number of cells, and you'll end up with a smaller time step because of these smaller cells. But by and large, Quadtree is a fantastic feature. It allows you to really put the detail where you want it. So both Subgrid Sampling and Quadtree can be used in combination, and it really is become a game changer. And the reasons for that in the urban world are the capturing of inlet flows is much more accurate. So the amount of water going into this inlet is picked up much more nicely by having subgrid sampling. You can see all the little dots there on the screen. That's where the levels have been sampled to build up the topography underneath these 2D cells. And of course, the other big benefit has been Quadtree. So what Quadtree allows you to do, it really allows you to get higher resolution modeling in terms of the flow patterns. So if you're really interested in where the water is moving and you want to model that in good detail, in this case here we've got a bit of a flow coming down a road, forcing a bit of circulation, spinning into this stormwater inlet. So that's what Quadtree will do. It gives you that high resolution flow patterns. If you need that, then that's a really good solution for it. And what all this means is that we are being much more realistic in our modeling. So if you've got features like this, you can pick them up with this combination of Quadtree and subgrid sampling. It really has become a game changer. So I'm now going to hand over to Rob to give a demo on using SGS and Quadtree in 12D. And as you'll see, it's pretty simple and straightforward. So over to you, Rob.
Thank you very much for that, Bill. What we're going to do now is give a short presentation of how 12D Model implements SGS and Quadtree. In the Quadtree slides that Bill has already showed you, there is often a polygon wrapped around the road where we wanted the finer grid. To show you how we create that inside 12D, because we do have road design strings, we've got this option under Utilities down to A to G, and it's called a boundary polygon. And what a boundary polygon does is it goes and wraps a polygon around a set of strings on a view. So I'm working with this view called Design right now, and I've gone and put this length of 1 meter, which means it'll get inside holes as long as they're bigger than 1 meter. Sometimes I put these little caps on the end, well actually I always do, to make sure that the polygon doesn't go inside the ends. But once you've got that little bit of prep work done, essentially all you need to do is to come and hit the Create button on that, and it's going to wrap that polygon around. Let me go add that onto this view so we can see what it looks like. It's in that model called QNL. And to make it a little bit easier to see, I'm going to go and turn those caps and the road design strings off. And then what's going to be left over is just that polygon that we discussed. Now there's 2 extra steps that I'm not going to go through. One of them is that polygon has to stay inside the 2D extents that we use for the project. So if I showed you that model, which is our urban extent, we would have to trim off this end of the polygon. And sometimes if you want TUFLOW to start up faster, you can filter some of these points out. So with that little bit of background into how to quickly create that string, Let's jump over to road flow and see how that's going to work for us. So I'm going to just pop up another view here that's got my inputs on it. And the first thing that road flow needs, those of you that haven't used it before, is that rectangle I alluded to on the outside. That's the extents of our analysis. We're going to have a 4-meter grid size to start with here, but here comes the part that we are talking about today, SGS frequency. So the side of every grid cell is going to have 9 points taken from the data train model and used to get those much better hydraulics that Bill's been talking about. Now down here we have specified our 12D finished surface tin, so that's where it's getting all the elevations from. And 12D will do all that for us. So that's the SGS side, pretty darn simple. Let's go across the optional tab and let's take a look now at the Quadtree. Essentially, this is, you notice it's not quite the same model. This is the trimmed off version that I see over here in yellow. And we are going to also be doing a rainfall on grid. So when we do our rainfall on grid, we are going to want to have our losses for the areas outside the road, and we want to have the area for the losses inside the roads. So pretty straightforward. We're only going to be running one of the AR&R 2019 storms, and we are going to be coupling it with our 1D network that you see inside here. So with all that set up and ready to go, we'll just go hit the run button on that. And we have to hit that run, there we go. And whenever you run road flow, the first thing it does is make sure that there's no results or files left from a previous run, so you're always starting from scratch. That first report that you see pop up there on the screen, what that is that's coming back from TUFLOW, telling us exactly what, they're called XF files, but essentially all the elevations that are needed for the run. And then 12D goes and creates what are called XF files. These XF files are TUFLOW's way of starting up very quickly. So 12D does all the data train modeling work. We leave TUFLOW to do the overland flow hydraulics. So this is a fairly short run. It's only going to be half an hour. And once that's done, we're going to read the results back in to take a look at it, and then that will conclude our presentation. Just about finished there. There's our 25 minutes. Once that closes, the last thing we'll need to do is to go in and read the results. So I'm just going to close that output window so we have a little bit more real estate to work with. We'll move across to our results tab. And because we're working with AR&R storms, if we had many storms, pardon me, wrong button there. If we had many storms, we'd have a log file for each one of our storms. But in this case, we've only run one storm. So I'm going to go just pick that one storm. And when we come down here to read results, it's going to bring in all the results so that we can view them inside 12D. So move that across just into the middle for ourselves. If we come over here to the plus button, what we're adding on to that view is what we call our grid tin results. So I'm going to add that on. And if I zoom in a little bit closer to one of these intersections, what you'll see is we've got that rainfall producing these velocities coming down to our sag inlets where the water is being captured. Few vortices happening in this area because there's so much water coming in the north before it goes and overtops the road. So that's what our results would look like in a plan view. If we then moved across into a 3D perspective view, I'm going to add on the same model. There, I can see it there for myself. And same results, but this time we're looking at them in a 3D perspective view. Now, I often show the results with this green water, and I get a little bit of flack from that from people from time to time. But just let you know that those color schemes are perfectly user-defined. So if I was to come up here to my legend and say, look, I'm interested in creating a new legend and a new range where the minimum color is 0, the maximum is 0.5, and I'm using some nice blues. if I was to go run that instead of having the typical green road water, which is probably more accurate for the color of road water, once it goes in and applies those new color schemes, you'll see it turns into a far better color of blue for those that like blue colored water. So that was just a very brief talk about how we implement both SGS and Quadtree into 12D road flow. And of course, the one part I haven't gone into is our more advanced features where we have our TUFLOW control files where we can actually do even more with TUFLOW. But we'll cut it off there for today and we'll turn it back to you, Bill.
Thanks, Rob. That was an excellent little demo of how you can apply subgrid sampling and Quadtree to the 12D model using TUFLOW. So let's have a look at a few other things that have been happening in TUFLOW world in recent times. So non-Newtonian flow. Well, this is one that is it's interesting because it's something a lot of people really don't even know about. But basically what happens when a fluid, its viscous characteristics change due to the forces that are applied. So this doesn't happen to water, but it happens to lots of other liquids. And by applying forces to it, then suddenly their viscosity or the just it starts to change. They become more like a slurry, or they might even become thinner. So there's some really weird and wonderful things start happening. And the equations that we use for solving how water moves around no longer apply anymore. And I won't get into those details. I'll leave that to the experts. But basically, a couple of examples are where tailings can, from a tailings dam, if you have a dam failure of a tailings dam, the tailings can liquefy and then subject to those gravitational forces, and then they can operate and move into a non-Newtonian flow mode. And another one is if, as an example, paint actually becomes thinner as you force it with a brush. And so paint's actually designed to do that. And that makes it much easier to put paint on a surface. And why we're interested in this is really there has been, as a consequence of, and this is the one in Brazil, a number of dam failures, particularly tailings dams or mining sites. And it's serious consequences that come from these. And we can't use our normal water flow equations to simulate these. So we have to use a different form of equations, and that's what we call non-Newtonian flow. And as you can see, this water is not really flowing like, this tailings slurry is not really flowing like water. It's, it basically working its way down. It's got a huge face in front of it, and it's more like a set of slurry or even like lava. So what you can do, you can now simulate those in TUFLOW. You do need quite a bit of experience or knowledge about what parameters to apply, because every non-Newtonian fluid is different to another non-Newtonian fluid. And what you see on the left here, here's the dam coming down. Now this is actually close to real time we're simulating. And on the right we have the plan view. So this is, it just rapidly, over 2 or 3 kilometers, it takes about 30 seconds to move. And around this point here, we actually speed up the animation to about 100 times. So now we're watching it propagate down 100 times faster than what it really did in reality. So just effectively, this will just keep going down and then it sort of comes to a bit of a stop as the pressure forces behind it subside. So it's pretty interesting stuff, pretty exciting, and these sort of functionalities are a very nice enhancement to TUFLOW the last year. And what's really cool is that you can do these amazing animations in 12D. The other little topic I'm just going to mention before we wrap up is basically modelling of bridge decks has always been somewhat problematic. And main roads in Queensland, Transport Main Road, have been working with us to try and improve how we represent bridge decks to start with. Bridge piers we're reasonably comfortable with. When it comes to bridge decks, there's still a fair bit of uncertainty about the parameters we should push into these models. And the reality is that it's quite a complex flow that's going on around the bridge deck. You've got water surcharging on this side. It's certainly not one-dimensional, it's certainly 2D, and it's even 3D effects going in the vertical. And to do this, we've been doing a range of modelling, so TUFLOW modelling, CFD modelling, and we have also, or Main Roads have arranged to measure data at a bridge site, which I'll show in a second. And as I mentioned earlier, it's a joint research exercise between ourselves and Main Roads. These slides are very much a courtesy of Urs, who's Manager Hydraulics and Flooding at the Transport Main Roads Department, Queensland Government. So there's been a couple of gauges installed at this site, Gordon Road Bridge. This is also via Moreton Bay Regional Council. And you see the bridge there, the gauges are being installed, and there's one on the upstream side and one on the downstream side. So they went in last year. We've only had one flood, unfortunately. We're really after a few more floods. So for this site, and they've done a good survey as well, for this site we've got a 12D TUFLOW model. You can see the flows coming down from left to right. There's the bridge there. Cross section here. Interesting to see a bit of a set down on this corner here, and that's occurring where you're getting these high velocities cutting in around this part of the bridge. We've also, or Main Roads have done a Flow 3D CFD model. So CFD models, for those unaware, is like your really high resolution modeling. And basically the equations they solve are pretty amazing, and they take a long time to simulate. So they're not really realistic to use for flood studies or urban inundation studies, but they can give some pretty powerful analysis of detailed flow situations. And another CFD package called OpenFoam, which we've sort of been doing as a bit of a cross-check of the process as well. So these three models have been built, and we've been running them, and some very early results that have been coming out of them are shown on this chart here. So you can see here, this is the bridge deck shaded behind. That's the rail through this height, and this is a bridge deck through here. What you're seeing here is basically the upstream water level and the downstream water level. So if the water level essentially is unchanged across the bridge deck, it would follow that dashed line. But as we expect, there is actually a bit of an afflux, and the yellow dots are from the one flood that we've measured. It's reached about this height here. So you can see once the water hits the bridge deck, the afflux starts to build up due to that bridge deck. We've also been doing and testing a range of TUFLOW methods. The sort of TUFLOW standard that's been used is sort of coming in along this line here, and we've been coming up. Of interest is that we did a similar sort of calibration exercise on the Iowa Bridge in Iowa and USA, and we've just taken those parameters and applied them here. And that's sort of the darker lines using a couple of different methods. And yeah, it's actually showing a pretty good match with what data we have so far. The Flow 3D is the orange line here, and OpenFoam is the green line, which you can sort of see underneath here. So basically, we're getting reasonable sort of consistency or match between the different methods. And what we're really wanting is hopefully this summer, and hopefully they're not bad floods, but we would really love to get some more data that pushes those yellow dots up into this space in here, so we can just do some more benchmarking and fine-tuning of how we would recommend modelling bridge decks. It's something that's been desperately in need for the industry for a long time, so we're pretty excited that we're getting this far down the track. So just to wrap up, in conclusion, basically subgrid sampling, Quadtree, has become a real game changer for urban modelling. It's allowing us to really drill into detail to model things like SUDS and WUSD features. It's as you can see on the animation here, you can really get down to that detail at a fine resolution where you need it and get better topographic representation with subgrid sampling. As I mentioned earlier, inlet flow capture is much improved, and in terms of modelling roads and gutters, it really does help enormously. So it is a game changer. Future features, we're building in groundwater and interflow at the moment. That's going to be really nice for catchment modelling, and Rob's planning to make use of those. Particle tracking and sediment transport are a couple of other big functionalities that we're building in. On the particle tracking is a nice one. So basically, you can feed into TUFLOW thousands of particles, and then you can sort of track where they've been, collect information on how fast they've moved, and lots of other things. And that way you can get a bit of a time history of where your water's been and what's been happening. That's a feature we're already using in our flexible mesh solver for our coastal estuarine modelling, and we've planned to bring that across to our fixed grid modelling as well. Anyway, lots of exciting things happening, and I hope you enjoyed the presentation, and thanks to Rob for all his efforts producing some of these beautiful images, and hope to see you using TUFLOW with 12D in the future. Thank you.